There's a question that has haunted humanity since the moment we first looked up at the night sky. It's a question so fundamental, so primal, that it feels almost childlike in its simplicity. Yet it leads us to the deepest mysteries of existence itself. Where does the universe end? What lies at the edge of everything? Is there a wall somewhere out there in the darkness? A final frontier where space itself comes to a close? Or does it stretch on forever, infinite and unbounded, with no end and no beginning? Tonight we're going to chase that question into the farthest reaches of space and time. We'll journey to the observable edge of creation, peer into the first light that ever shone, and confront the strange and beautiful reality that our universe may not have an edge at all, at least not in the way we imagine it. This is a story about horizons we can never cross, about light that will never reach us, and about the humbling realization that everything we can see, every star and galaxy in our night sky, may be nothing more than a tiny island in an ocean so vast it defies all comprehension. The edge we seek is not a place. It's not a destination we could reach in a spacecraft, no matter how advanced our technology becomes. The edge of the universe, as we'll discover, is something far stranger. It's a boundary woven from the fabric of time itself, a horizon created not by walls or barriers, but by the finite speed of light and the finite age of the cosmos. And beyond that horizon lies a mystery that may forever remain beyond our grasp. The ancient question. Let's begin where all good cosmic journeys begin, with our own deeply rooted human intuition. Everything in our earthly experience has an edge. The field where you might have played as a child has a fence that marks its boundary. The ocean, vast as it seems when you stand on the shore, meets the beach in a perfect line. Your room has walls. Your city has limits. Your country has borders. The very planet beneath your feet, though it seems endless when you walk across it, is in fact a sphere with a definite surface area and a specific, measurable size. We are creatures built by evolution to navigate a world of boundaries. Our brains are wired to expect that everything has a beginning and an end, an inside and an outside, a here and a there. It's the most natural thing in the world to project this fundamental understanding outward, to assume that the cosmos itself, the grand container of all things, must also have an edge. Somewhere out there in the darkness, we imagine, there must be a final shoreline, a last star, a point beyond which, what? Nothing? Emptiness? Something else entirely? For thousands of years, our ancestors tried to answer this question with the tools they had available: imagination, philosophy, and careful observation of the sky. The ancient Greeks, those brilliant pioneers of rational thought, were among the first to grapple seriously with the problem. Some imagined the universe as a great sphere, with the Earth at its center and the stars fixed to a crystalline dome that rotated overhead. Beyond that dome, most didn't dare to speculate. It was the edge of existence, the boundary between the cosmos and whatever lay outside it, if anything could be said to lie outside existence itself. Others, more daring in their thinking, proposed that the universe might be infinite. The philosopher Lucretius, writing in the 1st century before the Common Era, used a thought experiment that's still compelling today. He asked his readers to imagine traveling to what they believed was the edge of the universe and try to throw a spear past it. If the spear flies onward, then clearly you haven't reached the edge yet. But if something stops the spear, then that something is part of the universe, and once again you're not at the edge. The logic seems inescapable. Either way you turn it, The universe must extend beyond whatever boundary you propose. Yet even Lucretius couldn't fully escape the fundamental problem. If the universe is truly infinite, stretching on without end in all directions, then it contains an infinite number of stars. And if it contains an infinite number of stars, each pouring light into space, then why is the night sky dark? Why isn't every point in the sky blazing with starlight? This puzzle, which wouldn't be properly articulated until the 19th century when it became known as Olbers' paradox, hints at something profound. That our intuitions about infinity and edges might be leading us astray. The first revolution. Measuring the cosmos. For most of human history, the question of the universe's edge remained trapped in the realm of philosophy. We simply lacked the tools to measure the cosmos with any precision. The stars were mysterious points of light, their distances unknowable, their nature a matter of pure speculation. Were they small lights hung just beyond the moon, or were they distant suns like our own? Without a way to measure, we couldn't know. That began to change in the 17th century with the development of the telescope. Suddenly, the heavens opened up in ways that would have been unimaginable to the ancients. Galileo turned his primitive telescope to the sky in 1609 and saw mountains on the moon, spots on the sun, and moons orbiting Jupiter. More importantly for our story, he saw that the Milky Way, that misty band of light stretching across the night sky, was not a cloud or atmospheric phenomenon, but an enormous collection of individual stars, so numerous and so distant that they blurred together into a continuous glow. The universe, it seemed, was far larger than anyone had imagined. But how much larger? In the centuries that followed, astronomers developed increasingly clever methods to measure cosmic distances. They used parallax, the apparent shift in a star's position as Earth orbits the Sun, to determine that even the nearest stars were trillions of miles away. They discovered that our Sun was just one star among hundreds of billions in a vast flattened disk of stars we call the Milky Way galaxy. And by the early 20th century, they were grappling with mysterious spiral nebulae, fuzzy patches of light, whose nature was hotly debated. Were these spiral nebulae small clouds of gas within our galaxy, or were they island universes, entire galaxies like our own Milky Way, but at unimaginable distances? The debate raged until the 1920s when astronomer Edwin Hubble, using the newly completed 100-inch Hooker telescope on Mount Wilson, finally settled the question. He identified individual variable stars in the Andromeda Nebula stars whose brightness changed in a predictable pattern and used their properties to calculate the distance. The result was shocking. Andromeda was nearly 1 million light-years away, far beyond the edges of the Milky Way. In that single observation, the known universe expanded by a factor of billions. The Milky Way was not the universe. It was just one galaxy among countless others. And if there were galaxies stretching away into the distance as far as telescopes could see, then where did it all end? Had we simply pushed the edge farther away? Or was there no edge at all? But Hubble had an even more shocking discovery in store. As he and other astronomers measured the light from distant galaxies, they noticed something strange. The light was shifted toward the red end of the spectrum, shifted in the language of astronomy. And the farther away a galaxy was, the more its light was redshifted. According to the physics of light and motion, this meant the galaxies were moving away from us. Not just moving away, but the farther away they were, the faster they were receding. The universe, Hubble announced in 1929, was expanding. Space itself was stretching, carrying galaxies apart from one another like dots painted on an inflating balloon. This observation would revolutionize our understanding of the cosmos and transform the question of the edge into something far more complex and strange than anyone had imagined. The expanding universe and the Big Bang. Picture a balloon with dots marked on its surface. As you inflate the balloon, what happens to the dots? They all move away from each other. And importantly, there's no single dot that's at the center of the expansion. From the perspective of any dot you choose, all the other dots appear to be moving away from it. The farther away a dot is, the more rubber there is between it and your chosen dot to stretch, so it appears to recede faster. This is exactly what we observe in the universe. Galaxies are moving away from us in all directions, and the farther away they are, the faster they're receding. But we're not at the center of this expansion. Every galaxy sees the same thing we see. An observer in the Andromeda galaxy, looking back at us, would see the Milky Way receding from them. And they would see distant galaxies in their sky receding even faster. The expansion has no center. It's happening everywhere at once. Now, here's where it gets profound. If the universe is expanding, that means it was smaller in the past. Yesterday, the galaxies were a tiny bit closer together. 1 million years ago, they were much closer. 1 billion years ago, even more so. Run the clock backward far enough, and you arrive at a moment when all the matter and energy in the universe was compressed into an incredibly small, incredibly hot, incredibly dense state. The beginning, the origin, what we now call the Big Bang. The Big Bang wasn't an explosion in space, it was an explosion of space. At time zero, space itself began expanding from an infinitesimal point. There was no before the Big Bang because time itself began at that moment. And there was no where it happened because it happened everywhere. Every point in our current universe was, at that first instant, the same point. This might seem like an abstract mathematical concept, but it makes concrete, testable predictions. If the universe began in a hot, dense state and has been expanding and cooling ever since, then we should be able to detect the leftover heat from that primordial fire. And in 1964, that's exactly what Arno Penzias and Robert Wilson discovered, quite by accident, when they detected a faint microwave radiation coming from all directions in the sky. This cosmic microwave background, as it came to be known, is the cooled remnant of the Big Bang itself, now redshifted by the expansion of the universe to a frigid 2.725 degrees above absolute zero. The cosmic microwave background represents the oldest light in the universe, emitted when the cosmos was just 380,000 years old. Before that moment, the universe was so hot and dense that it was opaque, a roiling plasma where light couldn't travel more than a microscopic distance before being absorbed and re-emitted. But at 380,000 years, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Suddenly, the fog cleared, and light could travel freely for the first time. That light has been traveling through space ever since, and we detect it today as the cosmic microwave background. With the discovery of the Big Bang and the cosmic microwave background, we finally had a concrete age for the universe. Through careful measurements of the expansion rate and the properties of the background radiation, astronomers determined that the Big Bang occurred approximately 13.8 billion years ago. The universe has a birthday, and this seemingly simple fact has profound implications for our quest to find its edge. The observable universe, a sphere of light. If the universe is 13.8 billion years old, and light travels at a finite speed, roughly 300,000 kilometers per second, the fastest speed possible, then there's a fundamental limit to how far we can see. Light from objects more than 13.8 billion light-years away hasn't had time to reach us yet. It's still on its journey, crossing the vastness of space, but it simply hasn't arrived. Those distant regions of the universe are, for now, invisible to us. This defines what astronomers call the observable universe, a spherical bubble with us at the center, containing all the matter and light that we can possibly detect. But here's where things get counterintuitive. You might expect that this bubble has a radius of 13.8 billion light-years, matching the age of the universe. But remember, the universe has been expanding this entire time. A photon that began its journey toward us 13.8 billion years ago didn't travel through static space. The space it was traveling through was stretching, constantly lengthening its journey. Imagine you're a runner on a track, but someone is constantly stretching the track ahead of you as you run. Even if you're running at top speed, it takes you longer to reach the finish line because the finish line keeps moving farther away. Eventually you might reach it, but the track is now much longer than when you started. The same thing happens to light traveling through the expanding universe. Careful calculations taking into account the detailed history of cosmic expansion show that the edge of our observable universe, the most distant objects whose light is only now reaching us, are currently about 46.5 billion light-years away. The observable universe is thus a sphere roughly 93 billion light-years in diameter. Every photon, every piece of information from those distant regions has been traveling toward us for 13.8 billion years. But during that time, the expansion of space has pushed those regions much farther away. This is a crucial point that's worth dwelling on. When we look at a galaxy 10 billion light-years away, we're not seeing where that galaxy is today. We're seeing where it was 10 billion years ago, when the light we're receiving now left on its journey. During those 10 billion years, that galaxy has moved much farther away due to cosmic expansion. We're looking at a fossil, a snapshot frozen in time, and it gets even stranger. The farthest objects we can see are not galaxies at all. They're regions of the cosmic microwave background, the glowing remnant of the Big Bang itself. When we look at the cosmic microwave background in any direction, we're looking back to when the universe was just 380,000 years old. We're seeing the moment the universe first became transparent. We're literally seeing the edge of our visible history, not because there's nothing beyond it, but because the universe before that time was opaque to light. The cosmic microwave background forms a perfect sphere surrounding us at the edge of our observable universe. It's like a glowing wall at the horizon, marking the limits of what we can possibly see with electromagnetic radiation. Beyond that wall, the universe certainly exists. We have every reason to believe it continues on. But it's forever hidden from our view, cloaked in the opaque fog of the early universe. This is our first encounter with a genuine edge. Not an edge to the universe itself, but an edge to what we can observe. It's a horizon created by the finite speed of light and the finite age of the cosmos, a boundary that exists not in space, but in time. We're living inside an informational sphere, able to receive messages only from within a certain radius. Everything beyond that radius is, for now at least, unknowable. Look back time, telescopes, as time machines. To truly grasp the nature of the observable universe, we need to understand one of the most profound and poetic truths about astronomy. When we look at distant objects in space, we're not seeing them as they are now, but as they were in the past. Light takes time to travel, and the farther away something is, the longer its light has been traveling to reach us. Astronomers call this look-back time, and it transforms every telescope into a time machine. Consider our nearest celestial neighbor, the Moon. It's about 384,000 kilometers away, which means light from the Moon takes roughly 1.3 seconds to reach Earth. When you look at the Moon, you're seeing it as it was 1.3 seconds ago. It's a negligible difference, barely worth mentioning, but it's there. The Sun is much farther, about 150 million kilometers distant, so sunlight takes about 8 minutes to reach us. When you feel the warmth of sunshine on your face, that light began its journey 8 minutes ago. If the sun were to suddenly vanish, we wouldn't know for 8 full minutes. Now let's venture farther. The nearest star beyond our Sun, Proxima Centauri, is 4.24 light-years away. The light we see from it tonight left that star in early 2021. We're literally looking over 4 years into the past. When we look at stars within our own Milky Way galaxy, we're typically looking back tens, hundreds, or even thousands of years. The Milky Way itself is about 100,000 light-years across, so when we look at stars on the far side of our galaxy, we're seeing them as they were 100,000 years ago, long before human civilization began. But the real temporal journey begins when we look beyond our galaxy. The Andromeda Galaxy, our nearest major galactic neighbor, is about 2.5 million light-years away. The light reaching our telescopes tonight began its journey 2.5 million years ago, when our early human ancestors were just beginning to evolve in Africa. We're seeing Andromeda as it existed in the deep past. If alien astronomers in Andromeda were looking at Earth right now, they wouldn't see modern humans at all. They'd see a world populated by our distant evolutionary ancestors, Australopithecus afarensis, creatures that could walk upright but hadn't yet developed large brains or complex language. As we push our observations to more distant galaxies, we're looking progressively deeper into cosmic history. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. A galaxy 5 billion light-years away is seen as it was 5 billion years ago, before our Sun and Earth even existed. The most distant galaxies we've observed, spotted by powerful telescopes like the James Webb Space Telescope, are over 13 billion light-years away, meaning we're seeing them as they appeared just a few 100 million years after the Big Bang, in the universe's infancy. These ancient galaxies don't look like the majestic spiral galaxies we see nearby. They're smaller, more chaotic, still in the process of formation. We're watching the universe's adolescence, seeing the first generations of stars light up the darkness, witnessing the birth pangs of cosmic structure. And when we look at the cosmic microwave background, we're seeing the universe at just 380,000 years old, practically the moment of creation on cosmic timescales. This temporal aspect fundamentally changes how we think about the edge of the universe. The edge we can observe isn't a spatial edge, it's a temporal one. We can't see farther not because there's nothing there, but because we're running out of time. Beyond the cosmic microwave background, the universe existed, but it was opaque. We can't see it with light. The edge of our observable universe is the edge of our look-back time, the farthest point into the past that light can carry us. The cosmic horizon, forever beyond reach. Now we come to one of the most unsettling and profound realizations in all of cosmology. Not only is there a limit to what we can currently see, but there are parts of the universe that we will never see, ever. Not with more powerful telescopes, not with more advanced technology, not if we wait billions of years. They are forever beyond our reach, hidden behind a cosmic horizon that we can never cross. This might seem counterintuitive. After all, if the edge of our observable universe is determined by how far light has had time to travel since the Big Bang, shouldn't that edge keep expanding? Every year that passes, light from slightly more distant regions should reach us for the first time, pushing our observable horizon farther out. And in a sense, that's true. We are constantly receiving light from regions that were previously beyond our view. But here's the catch. The universe isn't just expanding, it's accelerating. This shocking discovery, made in 1998 by two independent teams of astronomers studying distant supernovae, completely changed our understanding of cosmic destiny. The expansion of space isn't slowing down as you might expect from the gravitational pull of all the matter in the universe. Instead, it's speeding up. Some mysterious force, which we've dubbed dark energy, is pushing space apart faster and faster with each passing moment. Dark energy is one of the deepest mysteries in physics. We don't know what it is. We don't know where it comes from. All we know is that it exists. It's causing the acceleration, and it makes up roughly 68% of the total energy content of the universe. Dark matter, the invisible substance whose gravity holds galaxies together, makes up about 27%. All the ordinary matter stars, planets, gas, dust, you, me, everything we can touch and see, constitutes a mere 5% of the cosmos. The implications of accelerating expansion are profound and unsettling. As space expands faster and faster, distant galaxies are receding from us at ever-increasing speeds. Galaxies that are sufficiently far away are receding at velocities that exceed the speed of light. Now, this might sound like a violation of Einstein's special relativity, which states that nothing can travel through space faster than light. But here's the key distinction. These galaxies aren't moving through space faster than light. Space itself is expanding between us and them, carrying them away on a cosmic current that has no speed limit. Imagine you're standing on one raft and trying to reach another raft floating in a river. The river is flowing, carrying the other raft away from you. If you can swim faster than the river flows, you'll eventually catch up. But if the river is flowing faster than you can swim, you'll never reach the other raft, no matter how hard you try. The water between you and your goal is being created faster than you can cross it. This is exactly what's happening with light from very distant galaxies. The light is traveling toward us at the speed of light, the cosmic speed limit. But space between us and the source is expanding so rapidly that the light is actually being carried away from us. It's like a runner on a treadmill that's moving backward faster than they can run forward. They're exerting maximum effort, but they're actually moving backward relative to the observer. For galaxies beyond a certain distance, currently about 15 billion light-years away, taking expansion into account, the expansion is so rapid that light emitted now will never reach us. Even though that light is racing toward us at 300,000 kilometers per second, the space between us and the source is expanding faster than that. Those galaxies have crossed what astronomers call the cosmic event horizon. They've moved into a region of space that is causally disconnected from us. Any light they emit now, or in the future, will never reach Earth. They're lost to us forever. This cosmic event horizon is constantly shrinking. As the universe continues to accelerate, more and more galaxies are being pushed beyond this boundary, crossing into the unreachable realm. Galaxies that we can observe today, galaxies whose ancient light is reaching us from billions of years ago, are in many cases already beyond the cosmic event horizon. We can see their past, but we can never see their future. They're ghosts, fossil images of objects that are forever beyond our reach. The shape of space geometry on cosmic scales. We've talked about the observable universe as if it were a simple sphere expanding outward from us in all directions. But the reality is more subtle. The true nature of the universe's geometry, its overall shape, depends on its density and composition, and it has profound implications for whether the universe is finite or infinite, bounded or unbounded. To understand this, we need to dive into one of Einstein's most revolutionary insights, the idea that space itself can be curved. In our everyday experience, we think of space as flat, a stage on which the drama of physics plays out, but not itself an active participant. Einstein showed that this intuition is wrong. Space, or more precisely, space-time is a flexible fabric that can be warped and bent by the presence of mass and energy. You can visualize this with the classic analogy of a rubber sheet. Imagine stretching a flat rubber sheet tight. That's flat space. Now place a bowling ball on the sheet. It creates a depression, a dip, a curvature in the rubber. That's what massive objects do to space-time. They curve it. The more massive the object, the deeper the curvature. A small marble rolling past the bowling ball will have its path deflected by the curvature. Not because the bowling ball is pulling on it with some mysterious force, but because the marble is simply following the straightest possible path across the curved surface. This is Einstein's explanation of gravity. It's not a force pulling objects together, but the geometry of curved space-time, telling objects how to move. The Earth orbits the Sun not because the Sun is pulling on it, but because the Sun's mass curves space-time, and the Earth is following a straight path through that curved space. A path we perceive as an orbit. Now, if individual objects like the Sun can curve the space around them on a local scale, what about all the matter and energy in the entire universe? On the largest scales, the collective mass energy of everything that exists must curve the overall geometry of the cosmos itself. The universe, taken as a whole, has a shape. But what shape? According to Einstein's equations, there are three possibilities, depending on the universe's density. If the universe contains exactly the right amount of matter and energy, what's called the critical density, then space is flat. two parallel lines drawn through this universe will remain parallel forever, just as they do in the Euclidean geometry you learned in school. A flat universe extends infinitely in all directions, with no curvature, no edges. If the universe contains more than the critical density, space has positive curvature. It's curved like the surface of a sphere. In a positively curved universe, parallel lines eventually converge and meet. If you could travel in a straight line through such a universe long enough, you'd eventually return to your starting point, having circumnavigated the entire cosmos. A positively curved universe is finite. It contains a finite volume, a finite amount of space, yet it has no edges. Just as an ant crawling on the surface of a basketball can walk forever without finding an edge, you could travel through a positively curved universe forever without hitting a wall. The third possibility is a universe with less than the critical density, giving space negative curvature, curved like a saddle. In a negatively curved universe, parallel lines diverge, moving apart as they extend. This universe is also infinite, but with a different geometry than flat space, one that allows for more volume within a given radius. So which type of universe do we live in? Astronomers have been working to answer this question for decades, using multiple lines of evidence. They study the cosmic microwave background, looking at the size of temperature fluctuations and how they correlate across the sky. They map the distribution of galaxies, measuring how matter has clumped together under gravity over billions of years. They observe distant supernovae to track the expansion history of the universe. All these measurements point to the same conclusion. The universe is flat, or extremely close to flat, within the limits of our observational precision. Studies by the Wilkinson microwave, anisotropy probe, and the European Planck satellite measured the curvature of space to exquisite precision, finding that if the universe is curved at all, the curvature is less than 0.4%, effectively indistinguishable from perfectly flat. A flat universe has mind-bending implications. It means that the universe almost certainly extends infinitely in all directions. The observable universe, our 93 billion light-year bubble, is just an infinitesimal patch of a boundless cosmos. Beyond our horizon, space continues forever, filled with more galaxies, more stars, more planets. If the universe is infinite, and if it's relatively uniform on large scales as observations suggest, then it contains an infinite number of galaxies, an infinite number of stars, an infinite number of planets. Everything that can happen does happen, infinitely many times. This flatness also suggests that we live in a special moment in cosmic history. In the early universe, dominated by matter and radiation, the density was much higher than the critical density. If left alone, the universe should have curved more and more over time. Instead, it remained stubbornly flat. The most elegant explanation for this remarkable coincidence is cosmic inflation, a brief period of exponential expansion in the universe's first fraction of a second that stretched space flat, like a balloon being inflated to enormous size. Cosmic inflation. The universe. Before the Bang. We've talked about the Big Bang as the beginning of the universe, the moment when space and time came into existence 13.8 billion years ago. But in truth, the Big Bang theory leaves many questions unanswered. Why is the universe so uniform? When we look at the cosmic microwave background in one direction of the sky, and then look in the complete opposite direction, we find that these two regions have almost exactly the same temperature, matching to within 1 part in 100,000. Yet these regions are so far apart, currently about 93 billion light-years, that they've never been in contact. Light has never had time to travel between them. How did they come to have the same temperature? And why is the universe so flat? As we've seen, a flat universe requires the density to be precisely balanced at the critical value. If the density were even slightly higher or lower in the early universe, the subsequent expansion would have magnified that difference, producing a universe that's clearly curved today. The fact that we measure the universe to be flat to within a fraction of a percent means the early universe must have been flat to 1 part in 10 to the power of 62. An absurdly precise fine-tuning that seems to demand an explanation. The answer to these puzzles came in the late 1970s and early 1980s with the theory of cosmic inflation, developed by physicists including Alan Guth, Andrei Linde, and Alexei Starobinsky. Inflation proposes that in the first tiny fraction of a second after the Big Bang, around 10 to the power of -36 seconds, the universe underwent a period of exponential expansion far more rapid than anything we see today. During this inflationary epoch, space doubled in size over and over again, perhaps 100 times or more in total. A region of space smaller than a subatomic particle was stretched to a size larger than the observable universe today. This sounds like science fiction, but it solves the puzzles beautifully. Before inflation, the entire observable universe today was compressed into a tiny region so small that all its parts were in close contact. Different regions could exchange energy and reach the same temperature, just as a well-stirred pot of soup becomes uniformly warm. Then inflation stretched this tiny uniform region to enormous size, preserving that uniformity across what is now our entire observable horizon. That's why opposite sides of our sky have the same temperature. They were once neighbors, intimately connected, before being separated by inflationary expansion. Inflation also explains the flatness of space. Any initial curvature would have been stretched almost completely flat by the exponential expansion, just as the surface of a balloon appears flatter and flatter the more you inflate it. If you inflated a balloon to the size of the observable universe, even the surface of a heavily wrinkled balloon would appear perfectly smooth and flat over any region we could observe. The evidence for inflation has been mounting for decades. It predicted the pattern of temperature fluctuations we see in the cosmic microwave background with remarkable precision. These tiny fluctuations, quantum ripples stretched to cosmic size by inflation, are the seeds from which all the structure in the universe grew. Galaxies, clusters of galaxies, the great cosmic web. Everything we see today traces its origin back to quantum fluctuations in the inflaton field during those first fractions of a second. But inflation raises a profound new question about the edge of the universe. If our observable universe is just a small patch of a much larger space that underwent inflation, how much larger is the full universe? The answer, according to inflation theory, is staggering. The entire cosmos could be at least 10 to the power of 23 times larger than the observable universe. That's a trillion times bigger. And it might be infinite. The multiverse, universes, beyond universes. Inflation does more than solve problems with the Big Bang theory. It opens a door to one of the most speculative and controversial ideas in modern cosmology, the multiverse. The idea is both elegant and unsettling. Our entire vast universe might be just one bubble in an infinite foam of other universes, each potentially with different properties, different laws of physics, different histories. Here's how it works. Inflation is driven by a hypothetical field called the inflaton field. In regions where this field has high energy, space inflates exponentially. When the inflaton field decays and its energy converts into ordinary matter and radiation, inflation ends and a normal universe like ours begins. This is what happened in our region of space 13.8 billion years ago. But here's the key insight. Inflation doesn't necessarily end everywhere at once. While inflation ended in our region, producing our Big Bang, it could continue in surrounding regions, and within those still inflating regions, other areas could decay and produce other Big Bangs, other universes. This process could continue indefinitely, with inflating regions spawning new universe bubbles, which are surrounded by still inflating space that spawns more bubbles, and so on forever. This scenario, called eternal inflation, predicts that our universe, our entire observable cosmos, with its billions of galaxies, is just one bubble in an infinite sea of universes. Each bubble has undergone its own Big Bang, has its own collection of galaxies and stars, perhaps even its own forms of life. But these other universes are forever beyond our reach. They're separated from us by regions of space that are still inflating, expanding faster than light, creating an impassable barrier between universes. What's more, these other universes might not be identical to ours. The laws of physics we observe, the strength of gravity, the mass of the electron, the speed of light, might be environmental properties specific to our bubble that differ in other regions. In the framework of string theory, there are an enormous number of possible ways for the fundamental forces and particles to be configured. Perhaps 10 to the power of 500 or more distinct possibilities. If eternal inflation is correct, all of these possibilities might be realized somewhere in the multiverse. This raises a profound question. Why do we live in a universe with laws so perfectly suited for the existence of stars, planets, and life? It might not be a coincidence at all. It might be that we live in one of the rare bubbles where the laws of physics permit complex structures to form, simply because those are the only universes where conscious observers can exist to ask the question. This is the anthropic principle. The idea that the universe appears fine-tuned for life, because only in such universes can life arise to notice the fine-tuning. The multiverse remains highly speculative. We have no direct evidence for other universes, and it's unclear whether we ever could. By definition, other universes are beyond our cosmic horizon, causally disconnected from us. Some scientists argue that the multiverse isn't even a scientific theory, because it makes no testable predictions. If anything can happen somewhere in the multiverse, then the multiverse can explain any observation, which means it explains nothing. Others counter that the multiverse is a natural consequence of our best theories, inflation and string theory, and that we should follow the theories where they lead. There are even proposals for how we might detect indirect evidence of other universes. If a neighboring universe bubble collided with ours in the distant past, it might have left a characteristic imprint on the cosmic microwave background, a kind of cosmic bruise we could potentially detect. For now, the multiverse remains at the frontier of scientific speculation, a tantalizing possibility that forces us to confront the limits of what we can know. The edge of our universe might not be an edge at all. It might be a boundary between bubbles, and beyond that boundary, an infinity of other worlds, forever beyond our view. Dark energy and the dying of the light. Let's return to dark energy, because this mysterious force has dire implications for the future of the universe and for the edge of what we can observe. We know dark energy exists because we observe its effects, the accelerating expansion of the universe. We know roughly how much of it there is. It comprises about 68% of the universe's total energy content. But we don't know what it is. The simplest explanation is that dark energy is a property of space itself, something called the cosmological constant, that represents a constant energy density, filling all of space. In this view, empty space isn't truly empty. It has energy, and this energy creates a repulsive gravitational effect that pushes space apart. As the universe expands and more space is created, more dark energy appears, driving the expansion to accelerate faster and faster. If dark energy truly is a cosmological constant, a fixed property of space that never changes, then the universe's fate is sealed. The expansion will accelerate forever. Galaxies that are currently within our observable horizon would be pushed across the cosmic event horizon, disappearing from view as they're carried away faster than light. The observable universe will actually shrink in terms of the number of galaxies it contains, even as it grows in terms of light-years of radius. This is already happening. Every second, thousands of galaxies cross the cosmic event horizon and become forever unreachable. The light we see from them tonight is ancient, emitted billions of years ago when they were still within reach. But the galaxies themselves have been carried beyond the horizon, into the unknowable beyond. Any light they emit now will never reach us. Over the next 100 billion years, this process will accelerate dramatically. Our local group of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions, is bound together by gravity, strong enough to resist the expansion. This small cluster will remain intact, but almost everything else will disappear. The distant galaxies we see today, the vast cosmic web of structure stretching to the horizon, will fade and vanish as they're pushed beyond our view. In 1 trillion years, the night sky will be almost completely dark. Our local group will have merged into a single large elliptical galaxy, and when astronomers of that distant future look out into space, they'll see nothing. No distant galaxies, no cosmic microwave background. It will have redshifted into undetectability. No evidence of the Big Bang. No evidence of cosmic expansion. They'll see only their own island galaxy surrounded by eternal darkness. If those future astronomers don't have access to our historical records, if they're starting from scratch, trying to understand the cosmos, they'll likely conclude that their galaxy is the entire universe, static and eternal, floating in an empty void. The evidence we have today for the Big Bang, for inflation, for the vast expanding cosmos, will be erased by dark energy's relentless acceleration. We are living in a special time, a brief cosmic moment when the universe is old enough to have formed galaxies and stars and planets and life, but young enough that we can still see the echoes of our origin. We can still detect the cosmic microwave background. We can still observe the expansion. We can still piece together the story of where we came from. In the far future, that privilege will be gone, and the universe will hide its own history from those who come after us. What lies beyond? So we return to our original question with a deeper understanding of its complexity. Where does the universe end? What lies at the edge? We've learned that the universe, as far as we can observe and measure, appears to be flat and very likely infinite in extent. There is no edge in the traditional sense, no wall or boundary where space comes to a stop. If you could somehow travel instantaneously across space, which physics forbids, you could go on forever in any direction, passing through an endless expanse of galaxies and clusters and cosmic voids. There is no edge to reach, no final destination, but there are horizons, multiple kinds of horizons, that bound what we can observe and interact with. The first is the particle horizon, the edge of our observable universe, currently about 46.5 billion light-years away. This is determined by the finite age of the universe and the finite speed of light. Light from beyond this distance simply hasn't had time to reach us yet. The second is the cosmic event horizon, determined by the accelerating expansion driven by dark energy. This lies closer than the particle horizon, at about 15 billion light-years. Galaxies beyond this boundary are receding so fast that light emitted from them now will never reach us. The expansion is carrying them away faster than their light can close the gap. Then there's the surface of last scattering, the cosmic microwave background, which marks the edge of what we can see with electromagnetic radiation. Beyond this lies the opaque plasma of the very early universe, forever hidden from our view. And if inflation and eternal inflation are correct, there may be other bubbles, other universes, separated from ours by eternally inflating space. These would constitute yet another kind of boundary. Not an edge to our universe, but boundaries between universes within the larger multiverse. So the edge of the universe isn't one thing, it's a collection of horizons, each defining a different kind of boundary. Some are observational limits that might recede as the universe ages and more light reaches us. Others, like the cosmic event horizon, are absolute barriers that we can never cross or see beyond, no matter how long we wait or how advanced our technology becomes. Perhaps most profoundly, the edge of the universe might be the edge of time itself. If the Big Bang was truly the beginning of time, then asking what lies before the Big Bang is like asking what lies north of the North Pole. It's a question that doesn't make sense because it applies a temporal concept to a situation where time doesn't exist. And if the universe is infinite in spatial extent, then the question of an edge in space is equally meaningless. An infinite universe has no center and no edge. Every point is, in a sense, the center, surrounded by an infinite expanse in all directions. We live in a cosmos that might have no boundaries at all, a cosmos that simply is, without edges or limits, stretching on forever.
Living at the edge.
There's a certain melancholy to these discoveries. We live in a vast, perhaps infinite cosmos, but we're forever confined to a tiny island of observable space. The observable universe, for all its staggering immensity, might represent an infinitesimally small fraction of what exists. Most of the universe is hidden from us, and much of it always will be. Dark energy ensures that the observable universe will shrink, in a sense, as more and more galaxies are pushed beyond our horizon. The amount of the universe we can interact with, the amount we can study and understand, is decreasing. We're living in a brief golden age, when we can still see the echoes of our cosmic origin, when we can still piece together the story of how everything came to be. But there's also something beautiful and awe-inspiring in this realization. We are, after all, part of the universe's conscious collections of atoms and molecules that have arranged themselves in such a way as to become aware of their own existence and to wonder about their place in the cosmos. We are the universe's way of knowing itself, of contemplating its own vastness and beauty. And what we've learned is extraordinary. In just a few centuries of scientific inquiry, we've measured the age of the cosmos, mapped its large-scale structure, peered back to its birth, and begun to understand the laws that govern its evolution. We know that we live in an expanding universe born in a hot Big Bang 13.8 billion years ago. We know that dark matter and dark energy dominate its contents. We know that cosmic inflation stretched the universe flat and seeded the structures we see today. We know that billions of galaxies populate the observable cosmos, each containing hundreds of billions of stars. The edge of the universe, we've discovered, is not a place but a perspective. It's the horizon of what we can know, limited by the speed of light and the age of the cosmos. It's a boundary in time more than space, marking the limits of our look-back view into cosmic history. It's a reminder of our place as finite beings in a possibly infinite cosmos, able to perceive only a small bubble of the whole. It was in that bubble, within our observable universe, lies enough wonder to occupy us for millennia. There are billions of galaxies to study, countless stars and planets to explore, fundamental mysteries to unravel. The edge of the universe might be forever beyond our reach, but the universe within our reach offers more than enough to inspire awe and fuel our curiosity. We began with a simple question: where does the universe end? And we've arrived at an answer far stranger and more beautiful than we could have imagined. The universe may have no end. It may stretch on infinitely in all directions, with no edges or boundaries. Or it may curve back on itself in ways we can't visualize, finite yet unbounded. It may be one bubble in an infinite multiverse, separated from other realities by barriers we can never cross. The edge, if it exists at all, is beyond our horizon, beyond the reach of light and time, beyond the power of any telescope we could ever build. It exists not as a physical barrier but as a limit to knowledge, a boundary defined by the fundamental properties of space and time themselves. We live inside an observable sphere 93 billion light-years across, a tiny bubble in a cosmos that might be infinite. And that's okay. That's more than enough. That's extraordinary. The cosmic perspective. As we wrap up this journey to the edge of everything, it's worth reflecting on what these discoveries mean for us as individuals, as a species, as conscious observers trying to make sense of our place in an almost unfathomably large universe. The cosmologist Carl Sagan once said that astronomy is a humbling and character-building experience. It's hard to disagree. When you truly grasp the scale of the cosmos, when you internalize the fact that there are more stars in the universe than grains of sand on all the beaches of Earth, that our entire galaxy is just one of hundreds of billions, that the observable universe might be an infinitesimal fraction of what exists, it changes your perspective. Our everyday concerns, the things that occupy our thoughts and dominate our lives, can seem terribly small against this cosmic backdrop. The arguments we have, the status we chase, the material possessions we accumulate, they all pale in significance when viewed from the cosmic shore. We're living on a small rocky planet orbiting an ordinary star in the outer reaches of a typical galaxy. In a universe so vast that our entire observable cosmos might be nothing more than a quantum fluctuation in an infinite multiverse. And yet, there's something profound in that smallness. We are small, yes, but we are also remarkable. Against all odds on this tiny world in the middle of nowhere, matter has organized itself in such a way as to become conscious, to look up at the stars, to wonder about its place in the cosmos. We are, in a very real sense, the universe awakening to itself, developing the capacity for self-reflection and understanding. Every atom in your body was forged in the heart of a star that lived and died long before the sun was born. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was created in stellar furnaces and scattered across space in supernova explosions. We are literally made of stardust, cosmic matter, that has evolved the ability to contemplate its own cosmic origin. This knowledge should fill us with a sense of connection to the Earth, to each other, to the cosmos itself. We're not separate from the universe, looking at it from the outside. We're part of it. We're deeply embedded in it. Our fate is tied to the fate of the cosmos. Our origins trace back to its beginning. Our existence is made possible by billions of years of cosmic evolution. The edge of the universe, whether it exists as a physical boundary or merely as the horizon of our observation, is also, in some sense, the edge of our knowledge. It's a reminder that there are things we may never know, questions we may never answer, and that's okay. The joy is in the journey, in the asking and the seeking, in pushing the boundaries of knowledge just a little bit further with each new discovery. We live in an extraordinary time. For all of human history, until very recently, the true nature of the cosmos was hidden from us. Our ancestors looked at the same stars we do, but they couldn't know what those stars were, how far away they were, or how the universe as a whole was structured. We're among the first generations to have this cosmic perspective, to understand our place in space and time. And we're living in a golden age for cosmic observation. Our telescopes can peer back to within a fraction of a second of the Big Bang. Our probes have visited every planet in the solar system. We've detected gravitational waves from colliding black holes, captured images of supermassive black holes at the centers of galaxies, and discovered thousands of planets orbiting other stars. We've measured the age and composition of the universe with remarkable precision. But there's so much we still don't know. Dark matter and dark energy together make up 95% of the universe. Yet we don't know what either of them are. We don't know if inflation really happened, though the evidence is strong. We don't know if the multiverse exists, or if it's even possible to find out. We don't know if the laws of physics are the same everywhere, or if they vary from place to place in the cosmos. We don't know if we're alone in the universe, or if life and intelligence are common or rare. These mysteries are what make cosmology exciting. They're what drive us to build bigger telescopes, more sensitive detectors, more powerful computers to simulate the evolution of the universe. They're what inspire each new generation of scientists to devote their lives to understanding the cosmos. The edge of our knowledge is constantly expanding, but it always reveals new horizons, new questions, new mysteries to explore. So where does the universe end? After everything we've explored, after journeying to the limits of space and time, what can we say? The universe in all likelihood has no end. It appears to be flat, which suggests it's infinite in spatial extent, stretching on forever in all directions with no edge or boundary. The edge we can observe, the particle horizon about 46.5 billion light-years away, is merely the limit of our vision, determined by the finite age of the universe and the finite speed of light. Beyond that horizon, the universe almost certainly continues, filled with more galaxies, more stars, more structure, extending possibly to infinity. But there are other edges, other horizons that bound our existence. The cosmic event horizon, pushed outward by dark energies' accelerating expansion, marks the boundary of what we can ever hope to interact with or observe. Galaxies beyond this horizon are lost to us forever, receding faster than light can travel. The cosmic microwave background marks the edge of what we can see with electromagnetic radiation, a glowing wall of ancient light beyond which the universe was opaque. And perhaps if inflation and the multiverse are real, our entire universe is just one bubble in an infinite sea of other universes, each with its own Big Bang, its own physics, its own story. The edge of our universe might be a boundary between bubbles, and beyond it, an infinity of other realities, forever beyond our reach. The edge of the universe isn't a place you can travel to. It's a horizon defined by the fundamental properties of space, time, and light. It's a boundary not of space but of knowledge, marking the limits of what we can observe and understand. And it's constantly shifting, receding in some ways as more ancient light reaches us, contracting in others as dark energy pushes distant galaxies beyond our reach. Perhaps most profoundly, the edge we've been seeking might not be out there at all. It might be within. The edge of our understanding, the boundary of our imagination, the limits of what our minds can grasp. We are finite beings trying to comprehend infinity, temporal creatures trying to understand eternity, small collections of atoms wondering about the nature of everything. And yet we've come so far. We've measured the age of the cosmos. We've mapped its structure. We've glimpsed its birth and forecast its fate. We've discovered that we live in an expanding universe, born in a hot Big Bang, dominated by dark matter and dark energy, shaped by cosmic inflation, possibly infinite in extent. We've found that the observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars, on scales of time and space that defy intuition. The edge of the universe, whether it exists as a physical boundary or merely as the horizon of observation, represents both the limits of our knowledge and the endless frontier of discovery. It's a reminder that no matter how much we learn, there's always more to discover, always new horizons to explore, always deeper mysteries waiting to be unraveled. And in the end, perhaps that's the most beautiful thing about our quest to find the edge of the universe. The journey itself, the asking and the seeking, the endless human drive to push beyond known boundaries and explore the unknown. That's what defines us as a species. We look up at the stars and we wonder. We build telescopes and equations and spacecraft to reach toward the infinite. We're not content with simple answers. We want to know everything, to understand it all, to reach the edge of the universe and see what lies beyond. We may never reach that final edge. The universe may be infinite, with no edges at all. Or the edges that exist may be forever beyond our reach, hidden behind horizons we can never cross. But that won't stop us from trying. It won't stop us from building bigger telescopes, asking deeper questions, pushing the boundaries of knowledge just a little bit further. Because we are explorers, we are seekers, we are the universe becoming conscious of itself and reaching out to understand its own vastness. And as long as there are mysteries to unravel, as long as there are horizons to chase, as long as there are edges to push beyond, we'll keep looking up at the stars and wondering what lies beyond. If you enjoyed this journey to the edge of everything, please hit that like button and subscribe to the channel. There's so much more to explore, from black holes and dark matter to the search for life beyond Earth. The universe is vast and strange and beautiful, and we're just getting started. Thanks for watching, and I'll see you in the next video.